Good morning. This is lecture number 10 on the second module on review of basic structural analysis. In this session we will complete approximate methods of lateral load analysis, and we will also do an introduction to displacement methods. So we will be finishing part 4 and starting part 5 of this book on structural analysis. You recall this last slide which we showed at the end of the previous class, and you realize that if the frame is symmetric due to the applied loading, lateral loading, you are bound to get points of contraflexure at the middle of all the beams, but we are not sure about the points of contraflexure in the columns, the location in the columns. This structure is statically indeterminate, and it would help if we could reduce or entirely remove the indeterminacy. So the idea is to do a quick approximate analysis. The other point that is obvious is because the columns, the two columns at any story deflect identically, they will have the same shear force and bending moment diagrams, and if this, so the story shear at any story level, considering cantilever action of that frame, must be shared equally by the two columns. So these 2 points are obvious. We need to make additional assumptions, and we will, this is the assumption we make. We assume that there are points of contraflexure in the middle of all the columns as well, which is an assumption that is valid only if the beams are infinitely stiff, as we saw in the earlier session.
So why would you assume that, isn't intuitively it is like the windward side should deflect more than the...
Why?
That is where the loading is coming directly.
Okay. By the way, if you really look at a building, that is also a misconception. Let us say the wind is blowing in this direction and you have a building here. It is true that there are forces acting, the wind pressures are acting directly on the windward face, but on the leeward side also there is some suction, right, and so really the whole building is affected by the wind field, and we have a concept of drag coefficient where you multiply the wind pressure with the drag coefficient and the exposed area, and you apply it for convenience on the windward face, but you recognize that it is actually including the leeward face as well, number one. Number two, the floor diaphragms ensure that all the frames participate. So effectively the whole building is moving as a whole, is it clear? And if you look at this superposition that we did, that is, we divided this loading into 2 parts, a symmetric part and an antisymmetric part, you will find that from the antisymmetric point of view there is a kind of antisymmetry. It does not matter which is the windward and which is the leeward. The only difference is the columns on the windward side will be subject to axial tension and the columns on the leeward side will be subject to axial compression, and the magnitude will be the same. So that is the overall behavior. We also assume that axial deformations are negligible. Okay, so we make this assumption, and let me come back to the point which seemed to trouble some of you in the last class. I want you to be totally convinced that that point of contraflexure will be exactly at mid height if we make the assumption of rigid beam, and I will go through it once more. Remember that I have just taken a column AB from somewhere in the building, and the point A is also not fixed really, A is also moving and B is moving relative to A. So we use the word interstory drift to talk about the relative deflection between B and A, the relative deflection between B and A. Is it clear? A is moving, but B, which is located higher, will move more than A, and we are really interested in the relative movement between B and A. Is it clear? That is called interstory drift. Now really speaking, you can put this guided roller support at the bottom also, because it is true, it is also going to move. So now this will give you a better idea of a symmetry in that frame, and of course it is unstable, so the rest of the building helps in propping it through. So this is the deflected shape, and we talk about a chord rotation phi AB, which is clockwise, and which is nothing but delta naught divided by h. Is it clear? So you look at the deflected shape and you can see straight away that the forces would be a pair of forces, not just one F. So it really does not matter where that F is acting, and it tells you that the shear force is constant throughout the height of the column, and not only that, you also get bending moments. What will be the bending moments? What will be the direction of the end moments? Clockwise or anti-clockwise? Anti-clockwise. And if you really want to look at it more closely, it is as though the top half behaves like a vertical cantilever fixed at the top end, and the bottom half behaves like another vertical cantilever fixed at the bottom end, and there are forces acting at the point of contraflexure, which is equal to F, and the end moments are Fh by 2. Is it clear? Now I hope you are totally convinced that if you make the rigid beam assumption, the points of contraflexure are going to be in the mid height of the column, and these are the values. Now so the total interstory drift delta naught is going to be shared by the top half and the lower half, and so that value is delta naught by 2, and if you take the simple moment the deflection equation, you get a relationship between delta naught and F, and it turns out delta naught is Fh cubed by 12 EIC. Clear? EIB is infinite in this assumption. Now if you draw the shear force diagram, it will be a constant, it will be equal to F, which in turn will be equal to 12 EI naught EIC divided by h cubed into delta naught, or 12 EIC by h squared into phi. Phi is delta naught by L. Clear? If you look at the bending moment diagram, how would it look? Well, you have two cantilevers there, it will look like this, drawn on the tension side, linearly varying with a point of contraflexure exactly at mid height, and the moment will be Fh by 2. So it turns out to be 6 EI by h squared into delta naught, or 6 EI by it should be h into phi. Is it clear? So these concepts you need to grasp early. Now let us try to do a quick approximate analysis of a 3-storied symmetric frame. Okay. Now it is given here that IB is equal to 2 IC, but for the approximate analysis we are really assuming IB is infinite. So that is the error we make in the analysis, right, and we will see later how to do a more accurate analysis of this using a displacement method. Now we will do two examples. First we will assume the base to be fixed at the bottom A and H, and the second example we will assume it to be hinged, and just to get you off the feeling that loads always act from left to right, we will reverse the loads and see how you draw the bending moment diagram. Okay. Okay, now take a look at this frame. If you assume hinges at the middle of all the beams, which is 100% accurate, and you assume hinges, internal hinges at the mid heights of all the columns, which is not accurate, which is a big assumption, you have actually introduced 9 moment release locations, right. If you look at this frame is statically indeterminate otherwise to the degree 9, and you have actually ended up making it statically determinate. So that is a tremendous simplification, but that makes your life easy. You can analyze this frame very easily. Where will you start? Okay, what was the first thing that you will you will calculate?
Support reaction.
So you need to draw the bending moment diagram. What's the first thing you will calculate? Support reactions. Okay, they will be shared equally. You get them, so it's 40 plus 40 plus 20, that's 100 divided by 2, 50, 50, fine. But to draw the bending moment diagram, you look at the story shear. Okay, the story shear you can do like that. I told you in the last class, you cut a section at mid height of the top story, you will find that that 20 kilonewton has to be shared equally by the two columns, you get 10, 10. Is it clear? What about the next story, the second story? There you are, it is 20 plus 40 divided by 2, you get 30, 30. And then the third one will be 50, 50. Is it clear? I have marked those arrows to show you the direction at the end of that element. Is it clear? This is an easy thing for you to do. Now that you have got this, can you get the column end moments? You just have to multiply the column shear by h by 2. That is all you have to do. So it is very easy. And so you can draw the shape of the bending moment diagram drawn on the tension side, and the lower story columns will have a moment 50 into 2, which is 100. The middle story will have 30 into 1.5, right, because the second story has a height of 3 meters, it turns out to be 45, and the top story column will have end moments equal to 10 into 1.5, which is 15. This much is clear. So you have got the column end moments. Now you need the beam end moments. How do you get that? How do you get that? So in your mind you must draw the free bodies. Let us take the top. You got a beam here, you have a column here. Remember we drew lines like this. So the column moment will be clockwise or anti-clockwise? It will be anti-clockwise, right? This is the top story, j or I, j equal to 1. So how much was this value? 15. So this was 15 kilonewton meter, this was 15 kilonewton meter. You had another identical column with the same moments, I am not going to write them down. Now equilibrium demands, or Newton's third law demands, that the beam end moment must be equal and opposite, so it will be clockwise, and it will also be equal to 15 kilonewton meter, both here and here. So it is as easy as that. So this is easy, it is this is going to be equal to that. What about the next level? So you have the second column, second beam, you have another column, this moment is, so all the column moments are anti-clockwise. What was this value? 45, this is also 45. So what do you think this should be? This should be clockwise, it should equilibrate. Now you can either subtract or add, I know that, but these are both anti-clockwise. When you join all the elements together, you should not have a nodal moment. So you have to add, not subtract, do not make that mistake. So it is 45 plus 15, which is 60. Is it clear? And the same thing holds good here. So you just need to do it at one end and it gets replicated. So it is very easy. What about the last one? It will be 100 plus 45, which is 145. So that is it. So it is very easy. Okay. Now you can also draw free bodies and draw the other shear forces, axial force. So it is so easy. A problem with a degree of indeterminacy of 9 is solved in 1 minute because we make these assumptions. We will see later how far off we are from the exact solution, okay, but this is good enough, right.
So if you work backwards, we know that a
Point of contraflexion for the beam will be at the midpoint. That's certain. So that can only happen, and given that the two beam end moments will be equal and opposite. So
which is stating the same thing. Point of contraflexion at the middle is stating that the two beam end moments will be equal with the same direction.
then if you draw the free body for the column, equal and opposite moments you put, then you get the point of contraflexion.
No, then you are assuming we know the beam end moment, we do not know the beam end moment. Okay, look at it very simply. Just putting the beam hinges reduces the indeterminacy from 9 to 6, still not enough to get a solution. So, right, it does not work. So, this is a beautiful logically meaningful method, but it is approximate. Now, let us ask a question, how do you calculate the drift in this frame? Because people would like to know how much the building will move on the top. You can also get the interstory drift. How do you do that? So that, okay, you can also get the beam shear. How do you get the beam shear? Well, if this is 15 and this is 15 and the span is how much? 6 meters, 6 meters. So you will have a vertical reaction like this, right? This is the couple which will, so what will be this value? It will be 15 into 2 by 6. Another way to put it is you have a hinge there, so you can draw arrows like that. So you could say this is nothing but this divided by 3. Okay, it is the same thing. So this is same as 15 divided by 3, which is 5. So you can work out the beam shears and so on and so forth. So now let us see how to calculate the drift. We have got the bending moment diagram. Can you tell me what D1 is approximately, given that the EI for the columns is some number 40,000 kilonewton meter squared? How do we proceed? Remember, we also found the deflection in a statically indeterminate truss in your assignment problem. Can you do something similar? Incidentally, the deflected shape that you are assuming is not this, but you are assuming this, because actually you are assuming the beams to be infinitely rigid. Is it clear? So you are going to get a solution for this frame where you are tacitly assuming IB is infinite for all this. How do you proceed? You apply a unit load F1 equal to 1, and do you analyze this frame all over again? Assume some of the forces to be 0. So, so this is the frame we need to analyze, and we do a clever thing. This is highly indeterminate, the degree of indeterminacy is 9. So let us cut the frame and let us expose some, how many redundancies do you expose there? 9, 3 at each location, a shear force, a bending moment and an axial force, and conveniently assume all of them to be 0. So you get a statically admissible solution. Can you draw the bending moment diagram for this frame? It is very easy, it is just a cantilever. So it will look like that, so easy, right? You agree? Simple. 1 into 10 is 10 at the bottom, and 1 into 3 is 3, 1 into 6 is 6, 3 values. Now this is your M1 diagram, and this is the unit load method. You invoke the principle of virtual work. So this was the original bending moment diagram. This is approximate. So the error in your answer is due to the error in this, not due to the error in small m1 diagram, but we live with that error. You know the actual deflection will be more than the value that you calculate, because the beams are not infinite, they are flexible, so they will add to the, you will get rotations theta, remember the earlier class. So it will be more, but this is a lower bound solution that you get. How do you proceed? Now you just multiply. I think you know how to do this, okay. So you take the leeward column, you are multiplying one triangle with, you could treat that as a trapezium. So remember the formula L by 6 and so on. So I hope you know how to do this calculation. I leave it to you to work out the details. Is it clear? So it is a quick, elegant, fast way of not only designing a frame but also estimating how much it will deflect. Now there are practical limits usually for that deflection in design, because you do not want the building to move too much. Roughly around height or interstory drift is limited to the height of that story divided by about 500 or so. Okay, now let us look at the second example. In the second example we assume the base to be hinged at A and H. Okay, so we should be showing hinges. So now do not go and put an internal hinge in the middle of the lower story, because that hinge is given at the bottom. Okay, hinge is given, so do not put another hinge, it will become unstable. So you do the same thing. I think it is pretty easy to do, but now you should draw the diagrams on the tension side. It will look this way. Is it clear? So do not be biased that the load should always act from left to right, they can act from right to left as well. Is it clear? So this problem is simple. Now let us take the more general problem of multi-story, multi-bay frames. Okay, and let us continue with the assumption that you have hinges, you have points of contraflexure in the middle of all the beams, which is not 100% true also, because it is not symmetric anymore, and in the mid heights of all the columns if the bottom is fixed. So these are big assumptions we make, but they are still not good enough to make the frame statically determinate. You can see that the indeterminacy can be generalized. If you have n bays and n stories, then the total indeterminacy is 3 times n bay 3 times into n story, which in this case is 3 into 4 into 3, 36. If you bring in those hinges, the points of contraflexure which are internal hinges, you get 12 in the beams and 15 in the columns, you get 27. You are still short of 9 additional conditions. So how would you solve this kind of frame? This is a problem which had troubled engineers in the early days when tall buildings were made, and many suggestions have been given. Can you give some? Let us go back to history and
Only the beam, like all the hinges.
sorry?
All the hinges in one floor make it as hinge support and down also.
I don't know.
Cut the buildings.
That we can cut it at the interstory mid height levels. That does not solve. What is the additional equation of equilibrium you are going to have? You need additional equations of condition. Is it clear? It is still statically indeterminate.
Compatibility equation.
Compatibility is you are just looking at equilibrium, statically indeterminate. You have already violated compatibility when you assumed hinges at the mid heights of all the members. So do not talk about compatibility. We want a quick rough solution. Remember, in the earlier case of a single bay multi-story frame which was symmetric, we made an assumption that all the columns share the story shear equally. Can we make something like that and do it? Can we make that assumption here? No. What do you think is more reasonable to make?
Total
Proportional to?
The distance from the.
Okay, so that's your method. You are saying that the total load is shared in proportion to the average bay width. So the exterior columns end up with less column shear than the interior columns, right? That was one proposal, but the one which gained more acceptance was one which said, which made it simple. It says let the exterior columns take half the shear of the interior columns, okay, and that is one way of doing it. So you will find historically two methods came into being. One is called the cantilever method, proposed by Wilson in 1908, the other is the Portal method proposed by Smith in 1915, and they actually made buildings which were very tall in reinforced concrete and in steel. Now let us look at both these methods and see how they simplify. Please note this whole method is approximate, you are ignoring completely compatibility, you are ignoring the relative stiffness of the beams and the columns. Okay. So let us look at the portal method. The assumption here is assume that each interior column resists twice as much shear force as each of the two exterior columns. Okay. You will find that this one simple assumption cracks the problem beautifully. Now let us take this example, I want you to do it, we will do it together. It is and I have given you an assignment of a similar kind. It is a 3-bay 2-storied frame. Usually the ground story will have a larger height because your foundation is located not at ground level but at some distance about a meter or 1.5 meters below the ground. Okay. So take this example and you can work on it. It helps if you have multiple colors in your pens because otherwise just take a look at it. How do we proceed? First you mark the hinges, okay, put little rounds in the middle of all the beams and middle of all the columns. Then you do what we did earlier, divide the story shear, okay, so you can do that, calculate the story shear, the top story shear is 20 kilonewton and the lower story is 20 plus 40 60, agree. How is that 20 shared by the 4 columns? If you had to give a formula, you look at that equation, you have to divide by 3 and you will get the interior column shear, right, and you divide, so you write that the interior column shears are 20 by 3. Why do we say 3? Because there are 2 interior columns and you get half contribution from the 2 external ones, so it is just number of bays. Is it clear? Do you agree to this? Clean, very easy to calculate, so you plug in those values, you got the column shear. Then for the exterior columns you put half this value, so 3.33 and 10. Is it clear? It is very simple, all of you getting it. So you start like this and what do you do next? You can get next the column end moments. How do you get them? Multiply these shears by half the respective story height. So you can mark them, they will all be anti-clockwise, remember our discussions, they will all be anti-clockwise, which means at the top of the column and the bottom of the column in any story you have to put equal numbers, and the exterior column will have a moment which will be half that of the interior column. So you have to do only one calculation and then multiply by 2. How much does it work out to? 3.33 into 3 by 2 is 5, 6.67 into 3 by 2 is 10. Is it clear? So you get 5 5, 10 10, 10 10, 5 5 in a minute. Any questions? Point of contraflexion, you made that assumption right in the beginning at mid height. Sorry?
If you take the extreme side beam,
Yep.
it's 50 and it's 10, it's 2 end moment.
We have not yet reached the beam end moment, we are looking only at the columns.
Yes, but eventually when
You do not go to eventually, go take one step at a time, otherwise you get confused. Are you with me till this stage? Is there any error in the calculation? Is it not straightforward? Can you not do it in 1 minute? Right? Now let us look at the big picture. So you can fill the bottom story also, 10 into 2 is 20, 20 into 2 is 40, right. So you got in one shot the column shears and column moments. Now we will see what to do. So it helps to draw a picture like this. Will you draw this? I have drawn all the free bodies. There are 3 beams on top, 3 beams at the first floor level, and there are 4 column segments in the 2 stories. We have calculated up to this much, we have calculated the shear force in the columns and the beam bending moments at the column ends. Yes? And if you have pens and pencils of different colors, it is very easy and very nice to do, so that when you look at it, it does not get crowded. Is this clear? All the directions are clear? Please note, all the column end moments will be anti-clockwise and all the beam end moments will be clockwise for reasons which we discussed earlier, and so there are few numbers only that you need to calculate. Are you with me now up to this stage? Right? Shear force in columns, bending moment at column ends we have calculated. What is the next step? And we have drawn the free body diagram. Bending moments at the ends of the beams. When you say bending moment in the beam, it varies linearly, it goes through 0 and changes sign. So bending moment at the ends of the beam. Okay. So how do we do that? You start at the top corner, maybe top left hand corner. You have to do only one calculation. Why? Because the same end moment travels through all the beams in any given flow. Let us check it out. Now take a look at this. You begin with this column end moment was 5, so this beam end moment must be 5, because the point of contraflexion in the middle, this must be 5, and if this is 10, this must be 10 minus 5, which is 5, and so on and so forth. So you will find that assumption by Smith, that the exterior column takes half the column shear compared to an interior column, greatly simplifies your calculation. You have only one beam end moment to calculate at every story. So you have done that, then you come here, you got 20 here, you got 5 there, so this will turn out to be 25, and therefore this must be 25, but this is 40, right? This is 40, but 40 and 10, please note, at that junction in this problem, okay, what was this moment anti-clockwise? Top one was 10 or 5? Column 5. No. Okay, what is this? This is how much? 20. And therefore this must be 25. Clear? So this is 25. This beam, what's the moment here? This is also 25 because all the beams will have the same moment. This was 2 times 5, which is 10, and this is 2 times 20, which is 40. 40 plus 20 minus 25 is 25. That is how you work out, but you do not need to do this because this will always work. You get only 25 in all the beams. Is it clear? So we worked out everything logically. Does it make sense? So it is very easy to do. So your beam ends, you get effortlessly the first floor, the beams right on top will have an end moment of 5, the beam at the middle level will have an end moment of 25. What is your next step if you want to finish this problem? After you find the beam end moments, what is deflection? Is the last. You are not asked deflection, you just want. Oh, you got all, you can draw the bending moment diagram, we will do that little later. Shear in which? Beam, because we have already got the shear in the columns. How do you get the shear force in the beam? Add the 2 end moments in the beam, divide by the span of the beam. So that is right, you guys are good, you can do this. So what do you get? 5 into 2 divided by 3 is 3.33. You got all the shear force in the top. 25 into 2 divided by 3, you got all the shear force. No, please note the shear forces are going to change because the span of the beam is different in different bays. So you have to do it carefully. 5 plus 5 divided by 3 is 3.33. 5 plus 5 divided by 4 is 2.5. 5 plus 5 divided by 5 is 2. Similarly for this. So please note the beam end moments are the same in all the bays in a given story, but the beam shear forces are different because the bay lengths are different in this particular problem. Is it clear? Are you with me? What's the next thing you can do? I mean, I want to find everything. Axial force in column. Perfect. How do you do that? So you see, I'm showing it step by step. How do you get? It's the same as the shear force in the beam here. So start at the left corner. If this is 3.33, this will point in the opposite direction. This is 3.33, and if the top is 3.33, then this must also be 3.33. It's in tension. Now you come here. You have to be careful. Upward 3.33, downward 2.5. So you need another downward 3.33 minus 2.5, which is 0.83. And if you got 0.83 there, then you must be getting 0.83 here also for equilibrium. Then you move to the next one. 2.5 upward, 2 downward. So the difference is 0.5. It must be downward because when you join all three, you should get 0. If this is 0.5, this will be 0.5 upward. And the last one, of course, it should match 2 and 2. Clear? Now you come below. You want to get this, you can work it out. Okay, I'm not giving you all the answers, you can easily work it. What's the next? So you got the column axial forces. What's the next step? What's the next step? Have you got everything? You can also find beam axial forces. How do you get that? Do you get it from column axial forces? Column shear. So you could have done it right in the beginning if you wanted. Okay, these are the other values. You could have done it right in the beginning if you wanted. But mind you, they are not very important. The most important thing is the column shear and the bending moment diagram. Okay, so the bending moment diagram is easy to draw. Points of contraflexion in the middle. I hope you understand this. And remember that the beam end moments are 2 times the column end moment. Is it clear? Portal method is easy. You can apply it to any problem that you get. So typically, if you are given any building, say 3-storied 4-bay building, it will look like this. You can work out formulas, but my suggestion is don't worry about any formula, just do it on the board, on the paper, because you won't get many big problems. In the cantilever method, which is a little more difficult, Wilson came up with the suggestion that you treat the frame as a cantilever beam. That means the whole building is treated as a cantilever beam, and you use simple bending theory to find the column axial stresses at story mid height that resists the story moment. So for convenience, let me rotate that frame by 90 degrees because we are more comfortable looking at cantilevers which are horizontal, right. So I have rotated the whole building 90 degrees in my mind and fixed the left end. So it's got an open web section. Do you understand? That means usual beams are one piece with solid cross section. This is an open web section. That means I have the solid areas only located at the column location if I cut a section anywhere, right. Is it clear? Now if I cut the section let us say at any line in the middle of any story, then I do not have any local bending moments in the columns, right, but I have only axial forces and shear forces. Let me plot the axial force variation. Well, according to this theory, we treat it as a linear variation assuming simple bending theory. It is like a truss, for example. Is it clear? But you have your beam has solid quantities here, here, here and here, and this is your stress distribution. Is it clear? Now it is obvious that you will have compression. Where will you have compression? At the bottom and tension at the top, and you have a neutral axis and so on. So you can use simple bending theory to calculate. And do you agree that the actual force in the column, axial force, will be the stress that you calculate from simple bending theory multiplied by the area of the cross section? You agree to that? So that is all. Now how do you get the stress? Go back to Euler-Bernoulli theory. M by I is equal to F by Y, right, or sigma by Y. So can we write sigma like that? M, here M is you are cutting the section at any story, so we need to talk about a story moment. See, do you agree? If I cut a section here, the moment I need to worry about in the beam, the bending moment in the beam is P6 into half this distance. Do you agree? So that is my story moment here. Like we had story shear, we can talk of story moment. If I am cutting the section here, the axial force here, then I have to multiply P6 into this distance plus P5 into that distance. So the story moments keep building up as I go to the ground floor, ground story. So you get the largest moments at the lowest end of the building. Is it clear? Now this formula, are you okay with sigma ji? I is the story level and I is the bay location and J is the story level. Do not worry about the formulas. Are you comfortable with this simple bending theory? M by I, and I is a property of that section, and the x bar by x j x I is your y. Now how do you get these properties? Well, it is just areas, centroids of areas and so on. So you can easily get the second moment of area, and if you substitute these formulas you will get a much more compact formula. Sigma is m by y. It's like let's say you replace that complicated frame with just one top chord and one bottom chord and the lever arm is y, then it is a bending moment divided by y. So this is an equivalent reduced lever arm y, which you can prove to be, using these formulas you can prove to be this quantity. I suggest you go through this carefully, understand these equations, and let us just directly apply it to the same problem so you get a feel for it. We are going back to the same problem. The portal method would have taken us 5 to 10 minutes to solve. Cantilever will take you a little more time. How do you begin? Well, first you need to assume something about the cross sectional areas. If nothing is given, you can assume all the areas are equal, but here we are told that the interior columns have twice as much area as the exterior columns. So you have 2A for the two interior columns and A for the exterior columns, right? Can you locate the centroid x bar? Will you do it quickly? What is x bar equal to? It is easy to do. You take moments of areas about the left edge. So it will be what? Total area is 2 plus 2 plus 2, 6A. 6A into x bar is equal to 2A into 3 plus 2A into 7 plus A into 12, right? Will you work it out? What do you get? Okay, 16 by 3 or 32 by 6, you get 5.333 meters. Clear? Easy to do. Now can you get the I value, second moment of area? You can do that. So basically you have to get yi. Okay, I have given you this formula, you know the location. Can I move faster? You can do these calculations, they are not difficult. The numerator is common for all the expressions, so you can calculate that, and you also need the story moments. Tell me what is the story moment in the top story? 20 into how much?
20
into 1.5 is your story moment. It is like cutting a section at the mid height where there are no local moments, so the total global moment in that second story is 20 into 1.5. What is the story moment in the lower story? 16, no, you can't do that. 20 into 5 plus 40 into 2, good, that is it. Clear? You do that and substitute these expressions, you can get, so every column, there are 4 column locations, right? Every column will have a different equivalent y, which is a property of that section, okay, and it turns out to be, if y is negative, it shows that it is not going to be tension, it is going to be compression, the force is going to be compression, that is it. Then you substitute there, you can get, you see we calculate y1, y2, y3, y4. y1 pertains to the column at the windward end, y4 pertains to the column at the leeward end, and y2 is for this and y3 is for this. M story is known, so you divide the M story by the appropriate value of y, so you get the force in the top column and the bottom column for the extreme windward column, for the next column, for the next column and next column. These are simple calculations too, but they take a little time, right. So you have got the column axial forces. If the column axial force is negative, what does it mean? It means that the column is in compression. So that is it. Once you have got, and you can check equilibrium, if you add all the forces, tension and compression at any story level, they should add up to 0, because there is no axial force on the building due to wind loading. So can you all do this step? Of course I will give you the choice, you can do either portal or cantilever. For the assignment you have to do the cantilever also, but in an exam it is too much to do. So you just do the assignment. In practice you can take, both are approximate. People say that the portal method is more accurate when you have a wider frame, not very tall, and the cantilever is more accurate when you have a very tall frame with narrow width, but it all depends on the relative areas. Okay, so here I will go quickly, we are doing the same thing. You have got the column axial forces. It is interesting, you really have a neutral axis somewhere in the middle. On one side you have tension, on the other side you have compression, so the arrows get reversed. Is it clear? We calculated these values. Now what do you do next? You got the axial force in the columns. In the portal method we got this last, here we are getting it first. Shear force in the beams. Can you do it? Just go in the reverse direction. You get the shear force in the beams. You get the shear force in the beams, right? What do you do next? Bending moment in the beam. If the shear force was the two end moments into span divided by 2, now you get the bending moment as shear force in the beam into half the span. Okay, so you can do that. So you get the bending moment at the beam ends, right. Please note the big difference between the portal method and the cantilever method is, here every beam in every bay will have potentially a different end moment, not like the portal method. Is it clear? Earlier you had to calculate only one beam end moment and the same thing spilled over everywhere. Here it does not happen because your shear forces are different, your spans are different, so this needs more work. Okay, but you know what to do. Once you have the beam shear forces, multiply the shear force by half the span of the beam, you get the moment. Clear? Have you understood? Portal method that way is much easier. Here you do much more calculation, but you can get the beam end moment. After you get the beam end moment, what do you do next? Column end moments by satisfying equilibrium. And what do you do after that? Column shear. See, you are getting the column shear at the fag end, and you can check equilibrium, and then you can put your shear force. You can get the shear force in the columns also. Is it clear? Please try this out, and if you can also get the axial force in the beams, but they are not very important. So these are the answers we got. If you compare these answers with the portal method, you will find that there are a lot of variations. Which is more correct? We don't know. We don't know. Seems to be, with your great experience you are saying that the portal method is more accurate. We don't know. So we will do this by matrix methods and see which is more accurate. There have been improvements on these methods, and people have, there is a method called factor method which tries to include the effect of relative stiffness of beam and column, but it takes away the beauty and simplicity of these methods. So in summary, the portal method begins with bending moment at the column ends and ends with the axial force in the columns and axial force in the beams. the cantilever method begins with axial force in the columns and ends with shear force in columns and axial force in the beams. Is it clear? Broadly this is the difference. So our time has run out. We will now look at the next topic in the next class, that is we are going to look at displacement methods, an introduction in the next class. Thank you.